In this video, we will be viewing a demonstration of the atomic emission spectra of three elements: hydrogen, helium, and neon. We will be observing that different colors of light come out of tubes filled with the different gases when they are excited by applying an external electric charge. We'll be able to separate each spectrum into its component colors using a very simple diffraction grating. Recall that a continuous spectrum of white light can be separated into its component colors by a glass prism. The prism bends the light, and some colors of the light are bent more than others due to differences in their wavelengths. We are observing the same process when droplets of water in the atmosphere separate sunlight into its component colors. The sun produces white light because it is an example of an incredibly hot object. But what about the light produced here on Earth by the chemical elements? For example, most of you are familiar with the term neon sign. What color of light does neon produce? Do other elements produce different colors of light? Are all of these lights filled with neon? What about these? Are these light tubes filled with the gas neon? First, let's look at what we call white light using a simple light bulb. When the tungsten filament light bulb is brightly lit, we can see a continuous spectrum of visible colors. Before we jump straight to neon lights, let's start with the simplest element, hydrogen. When hydrogen is given sufficient energy, it also produces visible light. The light from hydrogen is especially important in astronomy because much of the matter in the universe is made from hydrogen. Here is what a giant lit up hydrogen gas discharge tube looks like. As you can see, the lamp itself glows with a bright pinkish purple color. This is an example of the smaller discharge tube that we'll be using in this experiment. At the end of each experiment, we will scan back so that you can see the tube itself and the apparatus that we're using to apply the electric charge to the tube. In this case, they have little clamps which are going to an electric source. Here is some video footage we took of our small hydrogen lamp. First is the lamp itself over on the right. If we pass that light through a grating, we can separate that pinkish purple composite light we observe with our eyes into its component colors. You can see some bright vertical lines of different colors separated by dark black spaces. Other than the pinkish purple lamp itself, what colored lines are you observing? It makes sense that we can see red and blue when we split colors apart, because red and blue mix together to make purple, the composite color of the lamplight. As you reported, we don't see all colors of the rainbow. Hydrogen's spectral discharge tube does not yield a continuous spectrum of visible light. The lines are some of the visible spectral lines for hydrogen. We see duplicated spectra here because the diffraction grating gives us first order, second order, and third order, etc. diffraction. If we pan back with the camera, then we can see the apparatus itself, which is a not very expensive cardboard box with a piece of grating film taped over a hole in it. As Dr. Lyle removes the box, you can see the light itself and its power supply. Next, let's look at some video footage we took of our helium lamp. This time we are starting with the lamp itself in the center. To the naked eye, this helium light is a different color than the hydrogen light was. It's bright pink, and you can see the bottom of the lamp if you look carefully. Again, there are duplicate spectra observable through the grating on either side of the lamp. Please tell me what you are observing. Is the helium lamp giving off more or less lines of color than the hydrogen lamp? Yes, hopefully you realize that more lines can be seen in the helium atomic emission spectrum than we saw for hydrogen. Finally is the neon light. Again, the lamp itself is in the center. To the naked eye, the neon light is very bright red. The spectrum that is showing up has lots of red and some magenta and yellow. This is one that everyone is familiar with as vintage red neon signs. In the United States, these signs are often used to advertise for the beverage beer. The camera has been panned back now so you can see the window we made in our cardboard box covered with the grating. And finally, the box with the grating taped to it is being pulled away so that you can see the light apparatus again. What we just watched was a demonstration of spectral tubes. The study of atomic and molecular spectra is a scientific specialty called spectroscopy. The electrons of each element were excited in a discharge tube using electricity. The energy from the electricity was converted to kinetic energy that allowed the electron to move further away from its atom's nucleus. But this excited state is a temporary state. As the excited electrons fell from this higher energy level back to another lower energy level closer to the nucleus, they emitted photons of light. That gave us the atomic emission spectrum, and we could see some of that spectrum in the visible light range. Each element has its own set of allowed energy levels for the electrons, and therefore each element will have its own set of colored lines. Tune in to the next lecture to learn more about the energetics of this process for the hydrogen atom. I can review what happened to the hydrogen atom using simple diagrams here. If I draw a very crude picture of the hydrogen atom with a dot in the center for the positively charged nucleus and a circle to show the sphere where the electron is orbiting, here's the electron. Initially, we put some energy into the system using the electricity from the light apparatus. When we did that, the electron had to respond by moving to higher energy. So what it did was it moved further away from its nucleus. So now the electron is in an excited state. It's further away from the nucleus than it needs to be. It then relaxed over time, and when it relaxes, it emits light. And it gets closer to its nucleus again so that it's back where it started from. We'll be reviewing this process in more detail in the next lecture, so please check it out.